Here's one of the homework problems that causes a lot of problems for people. I get asked about it quite a lot simply because the graduate student that wrote the chapter of the book was different from the graduate student that does the homework problems. And one of the things that I think it can confuse people, well, I'm getting ahead of myself here. Let's work through the problem. The problem asks two parts. The problem asks, A, what is the shape of dihydrogen sulfide? Then they ask, is it a polar molecule? Well, part A is easy. It's part B that causes the issue. So let's take a look together. Matter of fact, I think I actually even contradicted in lecture myself. But let's take a look at this example. Let's draw the shape. So we're going to add up our total number of valence electrons. We have 2 hydrogens. Each of them is contributing 1. We have 1 sulfur, each contributing 1 electron. So that gives us 2 electrons from hydrogen. We have 1 sulfur. Each sulfur has 6 valence electrons. So that gives us 8 to draw our structure with. Draw our skeletal. Hydrogen can't be the central atom, so hydrogen has to be. That costs us 4 valence electrons, 2 for each bond. That leaves us 4 valence electrons left over. We place those on our central atom. So now we've got our Lewis structure. We have 2 bonded, 2 unbonded, and that means that our shape is going to be bent. That's not the problem that most people have with this problem. They have a problem with the next one. And that's because the book contradicts itself very blatantly. All right, you go and you look up your electronegativity values. And here's where things become really confusing, I think. You look up the electronegativity values for sulfur. You find sulfur, I believe your book list says 2.6. You look up hydrogen. I have 2.2 on most periodic tables. Your book may list it as 2.1. If it does, forgive me. But you look at hydrogen 2.2, sulfur 2.6, and you get an electronegativity difference of 4.0. By our definitions, a 0.4 difference should be nonpolar. That's what your book tells you. And because your book tells you that, I tell you that in lecture. Because once you get that nonpolar bond, everything stops. Here's where things become murky. Electronegativity is a comparative concept, right? We view it as something hard and fast, but it's not. It's a comparative concept. Remember, Linus Pauling made the electronegativity values to be a comparative scale. These electronegativity values weren't something that came down from Mount Sinai with Moses. These were something that man made up to help compare these elements. Another good example would kind of be If you've watched any of the subjective sports, I call them, gymnastics, I think is the example that pops to most people's minds. They do a gymnastics performance, and these judges all assign these numbers according to a set criteria, but they kind of get different numbers. One person's 9.6, maybe another person's 10, maybe another person's 9.3. And you're saying, Dr. Kelly, I thought these electronegativity values were determined mathematically. They are. However, the interpretation of them is subjective. In other words, what can be considered polar and what can be considered non-polar is in the eye of the beholder. Your book gives you guidelines that they attempt to turn into a rule. However, somebody else may disagree with these rules. There is an electronegativity difference between sulfur and hydrogen, right? Sulfur and hydrogen have different electronegativity values. And while those values are very, very close together, so close together that they can play nicely, 2.6 is slightly a bigger kid, right? So it's probably going to get to play with the basketball a little bit more. So there is a very slight dipole moment running from hydrogen to that sulfur. It is very slight and very small. So small that most people would say it's functionally non-polar. But really, polarity is a declining, it's a comparative random scale, and something somebody else may consider polar, somebody else may consider non-polar. The only time you can really say that something is 100% non-polar is if it's an element bonded to itself. If you have hydrogen bonded to hydrogen, that's always going to be non-polar because there's no difference. Oxygen bonded to oxygen, there's no difference in electronegativity value, so it's going to be 100% non-polar. Anytime you have anything else bonded together, you can argue that there's a dipole moment. Most biochemists would say that carbon and hydrogen is also non-polar always. I think most organic chemists would agree with that as well. However, when you get into the art of pea chemistry, where things are being looked at very mathematically, very rigorously, there they'd say there's different electronegativity values, so there's going to be some degree of polarity. That's where things really begin to get murky. You can view polarity as a strictly mathematical function where does the molecule have a dipole moment? If the answer to that question is yes, then if the answer to that question is yes, then the molecule is polar. Well, because you have that slight difference between hydrogen and sulfur, and the arrows have a component that's passing the same way, you can argue that there is a net dipole moment in that direction. And therefore, the molecule is polar. Now, that violates the rules your book tells you. On an exam, if they had asked you this question, I would probably give you, well, I would give you points back. Hopefully, I've done my job and weeded it out of the test bank because my test banks are easier to edit than are your homework problems. So I couldn't remove this one from your homework problems. But basically, this problem does violate what your book told you, and it violates the strict rules that most books give you. However, there is a logic to why they answered the way they did. Basically, I spent the last 10 minutes telling you not to worry about this problem, so don't.